One talk only before lunch by Oliver Ernst. And please go.
Okay, thank you very much. I'd like to thank the organizers for inviting me here. I've had a great week and I've learned a lot. It's a pleasure being here. So this is joint work with Lorenzo Tamellini, who's in the audience, and Björn Sprungk, who was here until yesterday, and he'll be coming back soon. So if you want, you can also discuss these things with him. So this is high-dimensional collocation with the Lognormal diffusion, and I have to thank Chris Schwab and Ben Adcock for laying all the groundwork for me, and so I can be brief with a lot of things which have been said before. Take us lunch a little bit quicker. But there was a gap. There was one area which I'm glad that Ben Adcock didn't talk about, which is the interpolation scheme of things for high-dimensional problems, and so that's what I'd like to talk about today. So the plan, I'll sort of give the setting of the problem. This has been talked about before, so I can be a little bit brief with this. I'll talk about sparse polynomial approximation to set the notation and some of the formalisms, and then give you a flavor of the convergence analysis, and end with a numerical illustration of how our algorithms are performing for such a problem. And listening to the discussions on surrogates, emulators, and collocation this past week, I couldn't resist putting in an example of some calculations we did for a groundwater problem to invite criticism. So, yeah. Okay, so in case you were beginning to miss it, here's the stationary. Hasn't been on the screen today yet. So this is our model problem again. We have a random diffusion equation. So this is a mapping, a random mapping, a random or an abstract random variable, if you like, going from the abstract space to realizations in this function space L infinity on some bounded domain D. Okay, and the random field, we'll model it this way. So the more difficult problem is the log normal probability law. So we'll assume that the volume of the diffusion field is parameterized like this. So we have a nominal value, a nominal function phi 0, and we have a series where we have deterministic functions phi m. They can be the eigenfunctions of the Carl-Hundred-Love expansion, or they can be wavelets, any orthonormal system or non-orthonormal system like here. And here we have the random parameters. I call it psi m, and yeah, so we will always assume that these are standard models and independent. And so the objective now is to construct a response surface, or the deterministic dependence going from the sequence psi of parameters here, the random parameters, to the solution of the boundary value problem. That's an object in this function space H01 of D, where psi doesn't belong to the entire sequence space, so I'll use r to the power n to denote all real valued sequences, but it lives in a subspace which has to be sufficiently large. So that's the setting. We'd like to construct this mapping from the parameters so that whenever we have a realization of the random sequence, we have a realization of the diffusion, and we can solve the diffusion problem and have a realization of the solution. Okay, so just an overview of all the, or some of the solution approaches that are out there, and why we think collocation has its advantages. So there's all the sampling-based approaches. The nice thing about Monte Carlo and related schemes is that, of course, you can use legacy code. Every realization looks like whatever deterministic problem you have, and you can use all the software you have for that. Another very nice feature is, of course, that the convergence rate of these things is independent of dimension, but a little bit slow. And of course, if you do have smoothness, and by smoothness I mean the dependence of the solution on the random parameters, you can't take advantage of it. And another disadvantage, sometimes, not always of course, is that Monte Carlo can only give you expectations of various quantities, whereas some of these other methods will give you a full representation of the solution as a random field, and sometimes it's advantageous to have that. Now, the stochastic Galerkin method, or polynomial chaos approximation, has been talked about a lot. This is a very clean, mathematically elegant variational formulation in both the spatial variables and the parameter variables. If you have smooth dependence, so here, of course, that's one of the reasons why these methods were invented, you can get spectral accuracy if you have enough smooth dependence. There's a very nice, well-developed convergence theory and adaptivity theory for this, but it does have a few practical drawbacks. For one thing, this isn't even practical, so already the theory for the log normal case, the variational theory for the log normal case is a bit of a pain. You saw some features of that coming up in the talk by Martin Eigel this week. Practical problems, you have a fully coupled discrete problem. Of course, there are dedicated solvers that can handle this, but you really need to modify the code, so it's usually very intrusive, if you want to use that word. And having a nonlinear, spatially nonlinear problem causes even bigger headaches for stochastic Galerkin. So stochastic collocations, you have only check marks here, so that's nice. So computationally, it's like sampling. So again, you can use all your legacy code. Nonlinearity, I'm not gonna, we don't mean to say nonlinearity is harmless, but it has less of an impact when you're doing collocation. Spectral accuracy, again, is possible if you have smoothness. And now we also have convergence theory for the log normal case, which is nice. And we also have adaptive algorithms, so you can actually apply these. So this is where this talk will fit into the grand scheme of polynomial approximation. Someone who's not a numerical analyst might not even be familiar with the word collocation, even though it's often used. So I put down the definition, which I think expresses it quite well. So this is from Lambert's book on ordinary differential equations, and it says, collocation is an old idea, widely applicable in numerical analysis, and consists of choosing a function, usually a polynomial, and a set of collocation points, and then demanding that the function does, at the collocation points, whatever is necessary to make it mimic the behavior of the unknown function we are trying to approximate numerically. What a sentence. So it's usually used, collocation is usually used for differential equations or integral equations. And what makes it a little bit different for these parameter problems or stochastic problems is that essentially you want the solution to have a certain value at all the collocation points. And the collocation points are in the parameter value. So this makes it a lot like interpolation. So from a large distance, this is just an interpolation problem. It's a little bit different from the way collocation is usually used in numerical analysis. Okay, and for collocation, there's been a lot of work done in the last decade or so. So the first papers were here by Babushka's group, and Xu and Hesthaven proposed this idea. I'm not sure which of the two proposed the name. I think it was the first paper. I'm not sure. So here, the setting was a little bit restricted. So you had, there are two important distinctions. One is, how does the coefficient depend on the parameters? So the easy case is when this dependence is affine. And the other distinction is whether the parameter components are bounded or not. So this is the bounded and affine case. And it took a while to extend it to the I think there's a mistake here. There should be bounded. No, yeah. So the first bullet point says finite dimensional noise, and so this should be an n, not an n with a double stroke. So these are finitely many. So that's the third distinction. Finitely many random variables. Yeah, I almost threw myself there. Okay, And so this is the work here, and it took a little longer to extend it to the log-normal case. We've done some work in this direction. Then there's not collocation, but best n-term approximations, where you have an expansion of the function you like, and you reorder the expansion so that the terms are in decreasing order. And here you can actually do the infinite dimensional case, and there's work been done in the last few years. And for best n-term, there are results, very nice results for the infinite dimensional log-normal case. Now, there's also interest in a very related problem, particularly in terms of Bayesian inverse problems, where you'd like to do integration of the posterior with respect to the posterior distribution. And so there are a lot of quantitative problems in this area also, and there's work on this. And this is the area where the work that I'm going to talk about today is located. So this is the infinite dimensional log-normal problem for collocation. Okay, so this is the setting. So we're going to talk about just approximating a function f, not necessarily the solution of a boundary value problem. So gamma is the parameter domain, h is some abstract space where this function is mapping to. So the argument is psi, the function value is f of psi, and we assume that this is defined pointwise. So we can evaluate at points in this domain gamma. H is a Hilbert space with an inner product and a norm. And this sequence space where gamma lies carries the usual countable Gaussian product measure. And we assume that f has finite second moments, so the integral over the sequence space of the square of the Hilbert space norm is finite. And we assume that we have this Hilbert space L2 with respect to this product measure given like this. So you integrate over the sequence space with respect to this measure. We assume gamma is open and it carries a full measure, and f is in L2 with respect to this measure. So that's the setting. And so how do we do sparse polynomial approximation? So we represent f, since we're interested in the log-normal case, where the parameters range over the entire real axis, we'll be using Hermite polynomials. And so the basic building blocks are the tensorized Hermite polynomials. And they form an orthonormal basis of this L2 space, so we can expand f in the spaces, and the coefficients f nu are just these inner products in the usual way for a Fourier series. This is sometimes called the polynomial chaos expansion, but it's just a Fourier series with these multivariate Hermite polynomials as a basis. The Hermite polynomials are constructed from the univariate Hermite polynomials of degree k, and this index set nu, or the multi-indices, so we have each multi-index is a sequence of non-negative integers. Only finitely many of them are non-zero. Okay, we're using this zero norm to indicate the number of non-zero components. Okay, and you can look this up, for example, in the Acting Numerical article by Schwab and Gittleson, where they prove that this is actually an orthonormal basis of this L2 space. Okay, and then best n-term, you order these guys in decreasing order and truncate the series, and it's been proven that this gives you a dimension-independent rate, which is nice, but of course this is not a computable approximation. And the alternative that I'd like to talk about is to construct approximations to f based on essentially just simple Lagrange interpolation. Okay. So the first building block that you need to construct this interpolatory process are just standard basic numerical analysis univariate Lagrange interpolation operators. So we'll call them UK, and they map functions to polynomials of degree k in the usual way based on the Lagrange fundamental polynomials, which I'll denote by Lik. So k denotes the degree, and so for degree k we need a nodal set with k plus 1 nodes, which we distinct, so we number them from 0 to k, and the superscript indicates polynomial degree. Then we tensorize these. So the U with the boldface multi-index k is just a tensor polynomial, which is just the sum over all multi-indices I component-wise less than k of f evaluated at these nodes times the tensorized Lagrange polynomials. And these are the obvious thing. These are just the products here. The multivariate nodes are now the Cartesian products of the univariate node sets. And these products are always finite because only finitely many of these multi-indices are on 0, and in that case, the polynomial is just 1. Okay, so we've tensorized the Lagrange polynomials, and these are objects like this. So this is a two-dimensional example where we have the interpolation nodes here. These are the nodes that belong to this two basis functions, and we have just tensor product Lagrange interpolation. Okay, the next step is that we don't want to work with the multivariate Lagrange polynomials. We want to work with the detail operators. And these are just differences of delta k of successive univariate Lagrange interpolation operators. And of course, we have this telescopic identity where uk is just the previous one plus delta k, or just the sum of all the detail operators. And in the same way that we tensorize the Lagrange polynomials, we also tensorize these detail polynomials. And these map into this multivariate polynomial space. And we can characterize this space. Well, so this is the full tensor polynomial space. I'll call it QK. This is the usual terminology also used in the finite element literature. As the span of these monomials, multivariate monomials of power multi-index I. And yeah, these are all the powers where each component is at most km, and this is the m coordinate of this multi-index describing the space. So you can describe this space with the monomials, but it's the same space also. It's also spanned by the tensor product Lagrange interpolation polynomials, and it's also can also be characterized as the span of the multivariate tensorized Hermite polynomials. So these are all completely equivalent. So of course, this only prepares the ground for what we want to do now, namely, of course, this full tensor product is way too expensive. You hit the curse of dimensionality relatively quickly, and we'd like to sparsify. So this space is characterized by this multi-index k. K is in any of these finite multi-indices, and we'd like to sparsify it. That is, so we don't want to use the full multi-index set, but we'll use a subset, which we usually call capital lambda. And the sparse tensor product operator, we'll call U lambda, is simply the sum of all the multi-indices contained in the lambda set of the tensorized detail operators. And P lambda is the corresponding polynomial space. So now this sparsified tensor product operator only maps into this reduced polynomial space, which we can characterize as the span of all the monomials where the corresponding multi-index power belongs to this index set, lambda. Okay, so I mean, this idea of these detail operators is actually quite nice. So here's just a one-dimensional example. We have a function in black that we'd like to interpolate, and if we use the regular interpolation operator to Lagrange, here's the constant one, quadratic one. Well, actually, we're jumping. We're doubling the number of nodes. So a constant one, cubic one. The next one has 5 nodes, and the next one has 7 nodes. So these are the successive interpolants of this black function. And if you look over here, we have the detail operators. Delta 0 up to delta 3 applied to the same function. And you can see that the detail operators get successively smaller. So this is with Crenshaw-Curtis nodes. These are nested sequences of nodes. You can do the same thing with non-nested loads like Gauss-Legendre. We'll be using the Gauss-Hermite loads later, which are also not nested. And you see the same effect. They get small very quickly if the function that you're interpolating is very smooth. The most famous example of these sparse interpolation operators is the Smoljak construction. So here we select tensorized detail operators in such a way that we allow only multi-indices whose sum of components is bounded by a fixed level index called Q. You can rewrite these. This is a formula due to Vasilkovsky and Wozniakowski. You can rewrite them again as a linear combination of tensorized univariate interpolation operators. The coefficients are actually known, and as Chris mentioned in his talk, many of these are zero, and this is one way you can see this sparsification taking place. And here's again this idea of interpolatory. So actually, even though you've taken a lot of these multi-indices out, these are still interpolatory formulas. That is, at the grid points that remain, these interpolated approximations, these polynomial approximations still interpolate, but what you need for this is for the node sets to be nested. If they're not nested, you lose the interpolatory property, but of course it can be still seen as a good polynomial approximation. A common node sequence is just a double number of nodes from one univariate node set to the next, and you can derive cardinality bounds, which show you that, again, you still hit the cursive dimensionality with these. So these are the number of variables, and this is the level index. You still hit the cursive dimensionality with this more construction if you don't do something in addition to that. Here's just another graphical representation of full tensor against multivariate sparse Hermite nodes. So you see them growing here in the full tensor, and this type of node pattern is established for the sparse Smoljak construction for the Hermite nodes. And these, for the Smoljak construction, these are the combinations of tensor products that are allowed in the different terms in the sum. So you see you're always using a combination, so this is in 2D, of tensor products with a large number of variables. You get a large number of variables in one direction, you have a small number of variables in the other direction. So this is the type of pattern that you get. Okay, and so some important properties of these multi-index sets. We'll introduce a partial ordering on these multi-indices, so these are always component-wise. And the important property of these sets that you'd like to have is monotonicity. And that means an index set lambda is monotonic or monotone if you decrease any component of a multi-index that belongs to lambda, this also has to be in lambda. Another useful feature is this rectangular envelope of a multi-index called RNU, and these are just simply all the multi-indices which are component-wise equal to nu, and the number of elements here is just the product of 1 plus nu. Yeah, and it's easy to show that if you have a monotone set, you can write the multi-index set as a union of these rectangular envelopes. Okay, and for a lambda multi-index belonging to or a subset of a rectangular envelope like this, P lambda, the corresponding polynomial space, is just the sparsification of the full tensor associated with K. And we can express the polynomial space belonging to a multi-index set lambda in this way. Again, span of the monomials, span of the Hermite Lagrange interpolants, or span of the Hermite polynomials. You get the full tensor space if you take lambda to be one of these rectangular envelopes, and in this case, UK is just the full tensor of the detail operators. And an important feature that you'd like to use is that if you have a monotone multi-index set, then this sparsified collocation operator is exact. That is, it's the identity on the corresponding polynomial space. And detail operators which don't belong, or tensorized detail operators which don't belong to the multi-index set, they vanish for all these polynomials. And variations of this theorem have been proved in a number of places in this literature. Now here's another example. You've probably seen this before this week. So this is how you think about these multi-index spaces. This is a Smollett construction, sometimes called total degree, where you have these simplices or these triangular multi-index set. Here's the hyperbolic cross, where you bound the product of the two, so it thins out much more as you get away from the axes. And then here's one of these rectangular envelopes. Okay, so I wanted to talk about the convergence analysis after setting up all these properties here. And how does this work? So we have our function we'd like to approximate. We have a nested sequence of monotone multi-index sets, lambda n, where n denotes the cardinality of the multi-index set. And we'd like to establish a convergence rate, some positive number s, such that the L2 error between f and its collocation approximation is bounded by c times cardinality to the minus s. And it turns out that the crucial quantities to estimate the collocation error are the worst case approximation errors when you apply the collocation operator to one of the basis functions, the multivariate Hermite basis functions. So this is the L2 approximation error of u lambda applied to h nu. So this is c nu. So this is the supremum of all multi-index sets of finite cardinality, where you apply the corresponding collocation operator of this multi-index set to the fixed basis function h nu. And this soup is actually finite because a lot of these detail operators delta I applied to h nu actually vanish if I is not less or equal to nu, and so you can write this as a max. Okay, in a way, these C nus, these worst case approximation errors, they express the deviation of this operator here, this collocation operator, which is an oblique projection onto the polynomial space. So the deviation of this oblique projection from the orthogonal projection onto P lambda. And, I mean, if we were projecting orthogonally, these C nus would all be either 0 or 1. So this is where it deviates from just n term or just truncating the Fourier series. Okay, and with the help of these C nus, you can easily show that you can bound the approximation error just by the sum of all the neglected multi-indices. Here you have the Fourier coefficients, the norm of the Fourier coefficients, but they're all multiplied by these C nu. And this is a very easy consequence of monotonicity and the exactness of u lambda on p lambda. So here you have the error. Here you write this as the sum over all multi-indices. This is only non-zero outside of lambda. Then you do Cauchy-Schwarz, and then you plug in the definition of the C nus, and you get this bound. So this is an upper bound for the approximation error. And the tool of choice in this area is something called Stechkin's lemma. This is what a lot of these convergence results regarding best n-term approximation are based on. And this lemma provides a decay rate for the LQ tail of a sequence which is LP summable. So Q is greater than P, you have something that is LP summable, and you say something about the tail of the LQ tail of the summable sequence. So assume you have a sequence A nu and LP, and you denote by lambda n those multi-indices nu, which correspond to the n largest elements. So it's ordered decreasing. Then you can bound the remainder, so everything outside of this best n-term set, if you like, in LQ by the LP norm of the sequence times n plus 1 to the power minus s. So this is the rate, and the rate is 1 over p minus 1 over q, which is positive. Q is greater than p. And the only problem with applying Stechkin's limit in our situation is that this index set, if you take the n largest elements of the sequence, is not necessarily monotone. So this is the difficulty that you have to get around in convergence analysis. There are 2 remedies, essentially, for doing this. So one is, if you have the easiest thing, the most obvious thing, is if you can bound these guys by some other non-increasing sequence, then you have a bound, you can apply Stechkin's lemma to the bounding sequence, and that gives you a rate 1 over p minus 1. Stechkin applied to with q equals 1. And this is the idea from some of the earlier papers in this area, where you can actually bound these. And essentially, these are the cases where the parameters are bounded, the random or parameter variables are all bounded. And this is quite easy using Taylor's series or Legendre series. For the unbounded case, unbounded log-normal case, there are results by Bachmeier, Cohen, DeVore, and Migliorati, where they have this very, very elegant weighted L2 summability. So, and they show that this is enough to show convergence for the best n-term approximation. So it works like this. You have a weight sequence or weighting sequence, B nu, in such a way that if these are the Fourier coefficient norms, if you multiply, if you weight these with the square root of B nu, then this is still L2 summable. This is the one component. And the other one is a majorizing sequence C hat, which majorizes C over the square root of these weight sequences. And if you have those 2 things, the weighting sequence, so that this is L2, and a majorizing sequence, this implies a rate 1 over p minus a half, essentially by applying Stechkin's lemma now with q equals 2. So if you have these 2 things, it's very easy to prove that you have a rate. So the question is, how do we get these things for the collocation? This is, again, a sufficient condition. It's a little bit technical, so I won't go into too much detail, but just to give you a flavor of the type of smoothness assumptions you have to make to get this. So R is a non-negative integer, and you have another sequence, real sequence, positive tau m, and you can generate explicitly a sequence B nu such that you have this identity. So over here, here we have this weighted L2 series, and here you have partial derivatives. So here's where smoothness of the function that's being collocated comes in. Partial derivatives, and these look like Taylor coefficients. So the partial derivatives, the maximal index is bounded by R. So these are all partial derivatives up to order R in each variable. So this is in generally an infinite set of multi-indices. So this is a true, you want this to be finite. So this is a true convergence requirement. So the assumption is now, you have this positive sequence, which is LP measurable, such that this expression over here is finite. That's the assumption. So essentially this means the function has to possess partial derivatives, they have to be in L2, and you have to have these weighted sequences of these L2 norms be finite. It looks a little bit like mixed derivatives that you're used to from collocation bounds, but we're not really sure whether this might be just due to the technique of proof or whether this is actually really such a mixed derivative type of requirement. And it turns out that going back to the solution of the random diffusion equation, the log-normal diffusion equation, you can show that this assumption is satisfied if we have this kind of an assumption on the expansion functions. So these are the expansion functions of the diffusion coefficient, these deterministic functions. And if we weight them with the sequence tau m up here, and take the soup, and this is finite, for an LP summable sequence Gm, then this assumption is satisfied. Okay, so that means we have this weighted L2 summability, and now we only need this majorizing sequence. So once we have this, we have the sequence B nu, that gives us this sequence here, and we have to majorize this somehow. And so we have to essentially bound these C nus somehow. And this is where we tailor the method to the univariate Hermite polynomials. It turns out that if you can bound these detail operators applied to the Hermite polynomials, so these are the univariate Hermites, in such a way, with some parameter theta and some number k, then you can bound these C nus, these multivariate, multi-index C nus, in this way. Okay, and essentially that's it. That's the you get a majorizing sequence out of that. So the theorem is that if such a bound holds for the Hermite polynomials, or in general the expansion polynomials of your L2 space, then for any f which satisfies assumption A, and now we have to get the right relation between this index R and the assumption A, the P of the LP summability and the theta appearing in this bound, then you have existence of such a sequence lambda n, so that the corresponding collocation operator has this convergence rate. So what's left is to show something like this for the Hermites. And it turns out if you dig deep into the orthogonal polynomial literature on Hermite polynomials, you can show that such a bound exists. You can do this all explicitly. It turns out if you do some numerics, the numbers are much better than this bound, so we believe this can be improved, but we haven't been able to prove this yet, although it's a very, very simple statement about Hermite polynomials. For other node sequences that you'd like to use for collocation, for example, weighted layer points have the advantage that you can easily generate nested sequences of interpolation nodes. The Gauss-Hermite nodes, of course, are not nested. That causes some annoyances. But this is still open whether you can get a bound like this. Another thing you can show now, you'd like to, of course, be able to relate the convergence rate to the amount of work you have to do. The amount of work you have to do is depends on how many deterministic PDEs you have to solve, and this in turn depends on how many collocation points your corresponding sparse grid has associated with the multi-index set lambda. And it's easy to show if the nodes are nested, you'd have the cardinality be equal to the cardinality of the multi-index set. In the general non-nested case, an upper bound is the square of the cardinality of the multi-index set. And so if you translate the convergence result to the cardinality of this sparse grid node set, you get this rate. So you still get a positive rate, and you still have dimension-independent algebraic convergence. Okay, so here's a numerical illustration. So we have a 1D, spatially 1D boundary value problem. The coefficient A is given by this expansion, so the phi's are just sine functions. These are random parameters. And we have a parameter Q with which we can adjust the smoothness of this. So if Q equals 1, this is known as a Brownian bridge. For larger Q's, you can call this a smooth Brownian bridge. And so this corresponds to our setting with the phi m's equal to this damped sine function, and you can show that this requirement is satisfied for this example. And so you can immediately translate this to an expected convergence rate. In this case, we get, so this is this Q appearing here in the series, Q minus 1 over 2 minus 4 with respect to the number of multi-index nodes. So this is the convergence you should be expecting. Of course, we only have an existence result for the multi-index set. we haven't said anything about how to find this multi-index set. And so here are two algorithms with which you can construct such a multi-index set explicitly. And this is an idea that goes back to a method of Gessler and Kleebel. This is a greedy algorithm where you keep adding multi-indices to your multi-index set in such a way that you maintain monotonicity. And the new multi-index that you add maximizes some objective function h. So h is a heuristic for improving the approximation, and the candidate set for the new multi-indices is just the neighborhood of the current multi-index. So you can only look in the neighborhood of the multi-index set that you currently have in order to maintain monotonicity. So these are the only candidates, and so you explore this neighborhood, and there's two variants of this. One we can do a priori without computing any approximations. This goes back to this major rising sequence that we can construct, and there's another adaptive method where we use these deltas applied to u that we've computed, and so this is this profit approach. You want this to be as large as possible, so this is the expected gain in approximation. This is this detail operator applied to u, and this is the term that's proportional to the work. This is the size of the sparse grid associated with this multi-index u. So you explore the neighborhood, evaluate either this a priori or a posteriori quantity, and add those, the most promising ones, to your multi-index set. So this is what we did, and here are some runs. Here we have the case where q equals 1. So the theory says you should expect no convergence because the assumptions aren't satisfied, but we still have numerically, we're observing some convergence. We've measured an a priori rate of 0.4 and an a posteriori rate of 0.5. So the colors you see here, the green is the extended grid. The A is the grid, the multi-index set generated with the a posteriori adaptive algorithm, and the purple one is the one with the a priori heuristic. Extended grid means you're using all the computations you use to explore the boundary, the neighborhood set. And since you've had to solve PDEs to explore the boundary, you might as well use this information. So that gives you another convergence curve. Okay. And of course, we should see no convergence, but we're seeing some, so there's room for improvement in the estimate. Here's 1.5. We expect 0. We see 0.7 and 0.8. Q equals 2. Expect 0.25. See 1 and 1.1. And a very smooth case where convergence accelerates. So this is with respect to the number of the work, essentially, the number of PDEs you have to solve, and we have corresponding plots of convergence with respect to the size of the multi-index set. And we've also labeled these convergence curves with the number of variables which were activated. And so in this case, we were able to solve the problem using 249 variables for the a priori grid and 131 variables. So the algorithm picks automatically the variables it needs to activate among the infinitely many that there are. Here's some different convergence curves for the different smoothness, and we see that it accelerates like as we expect. Here's another plot which shows the interplay of infinite dimensions versus finite dimensions. So here we've solved the problem with a finite number of variables going from 10 to 160, and we see that the convergence rate is not independent of the dimension, so it goes faster for smaller dimensions, but as you increase the dimension more and more, it approaches this finite rate, so that you do have a finite rate which holds for all dimensions. Okay, so as a bonus for lunch, we solved, a while back, we solved some groundwater flow problems with a random conductivity for data that came from the waste isolation pilot plant WIP in Carlsbad, New Mexico. This is publicly available data. We're not associated in any way with the organization that runs WIP. But this is an operational nuclear waste depository, and there's an extensive amount of data available on the area. And it also turns out that there's a site assessment test case which involves a very, very simple groundwater flow problem where you have a lot of measurements of the uncertain quantities. So this is a blow-up of the geology. This is the repository, this is depth, and you have a bunch of geological layers, and they're all impermeable to groundwater except for this red one, which is very, very flat. And one of the interesting problems that the site assessment wanted to solve is that if there were a breach of the repository in the next 10,000 years, how long would it take for radioactive particles to reach the biosphere by groundwater transport through this layer? And so the uncertainty here is this hydraulic conductivity. So this is exactly the type of problem that leads. I mean, if you use Darcy flow, so the forward model is a finite element approximation of Darcy flow combined with particle tracking after you solve the PDE to get the travel time of particles going through this permeable layer by groundwater transport. So, I mean, geologists say you should model conductivity not as a Gaussian random field, but as a log-normal random field. And this is one of the reasons that people are so interested in log-normal random fields. But for diffusion problems, actually the geologists have really moved on, so this is no longer seen as state-of-the-art. So I guess the time of this problem is past. It's mathematically interesting, but I don't know how important it is for real life. Anyway, so what you do, so we have all these measurements. For example, we've conditioned an input log-normal field on observed data using essentially kriging. So here's a map looking down on the area. This dashed line is the repository, and here we have a kriging interpolant of the transmissivity, and we use that to essentially do a Monte Carlo simulation. So we sample the random parameters, we get a log transmissivity, we solve the PDE, we solve the transport problem, we get particle trace, we measure how long it takes. And so the quantity of interest is the travel time, and we're interested in the empirical CDF of the travel time, so the probability that the travel time associated with this random variable is less than some quantity t. And of course, you'd like a surrogate so as not to have to solve the PDE for each sample. And so in this work, which we hope to finally submit soon, we thought we would compare our collocation approximation, our sparse collocation, with a Gaussian process emulator. So this is essentially the contribution of Andrew Cliff, who was working with us in this project. And we tried to do our best. I learned this week that it's easy to construct a bad emulator. So we were probably very good at constructing bad emulators. But I learned a lot this week about how to calibrate them, validate them. So this is certainly something we'd have to revisit. But here's just some plots. So the ground truth is Monte Carlo. This is the black line. What you see here is the empirical CDF of the quantity of interest, travel time, log travel time. So 4 would be 10,000 years. 10,000 years is also the time duration that the regulatory committees or bodies require for the certification. So it's not uninteresting. So yeah, so these are the distributions, the travel time computed with Monte Carlo. So the red dashed line is a collocation approximation, and the green dashed line is a Gaussian emulator, and the dotted line is a direct collocation surrogate for the travel time. Now the red collocation surrogate was computed by solving the PDE with collocation, and then doing a travel time calculation for each realization. This one tried to do the travel time directly, but if you think about it a little, the travel time itself is a non-smooth function of the parameters. So it's to be expected that you don't have nearly enough smoothness for collocation to work well, and you do see this, that the direct collocation, as you increase the levels of the collocation approximation, deteriorates, so it doesn't even converge, which confirms the fact that you do need smoothness to benefit from collocation. So the green curve, the emulator, with the number is the number of design points. So here we're increasing the number of design points to keep these comparable. And I guess you can see that the collocation seems to follow the Monte Carlo solution quite well, whereas you can still see some deviation for the emulator. Another thing we tried was to apply a statistical test, the Kolmogorov-Smirnov test, to determine whether or not the random field or the random quantity obtained with the emulators or the collocation approximation are sampling from the same distribution as Monte Carlo. And so, yeah, in case of the collocation approximation, the check marks indicate that the test was passed, and in the case of the emulator, it didn't pass in the cases that we looked at, but it would certainly be interesting to see that whether if we applied all the techniques that I learned about this week to the emulator, we could improve the performance of the emulator. So this has certainly has been worthwhile for me to try to resolve these issues that we've seen. Okay.
Quick question.
Yes.
When you show the Gaussian process emulator, you're not showing the uncertainty about that Gaussian process emulator.
No.
You're only showing the mean from the Gaussian process emulator.
No,
So
this
if the
is the
uncertainty
CDF.
is
I mean,
large,
the uncertainty, this is the distribution. So
no, but the Gaussian process emulator is a stochastic thing, and it has a mean, but it also has an uncertainty about that mean. So you should have bands rather than
okay.
single lines, and I wonder whether that was so far away that it said it was going to be that far away and was in the uncertainty bound, or whether the uncertainty bound is much smaller than that.
Yeah, but this is not the quantity. This is the distribution function, which is a deterministic object, right?
Well, it depends how you sample from that Gaussian process emulator to get that deterministic object.
Yes. So the emulator is a stochastic thing, and the quantity derived from the emulator is a random variable. It has a distribution, and its distribution function is a function. There's nothing stochastic about that anymore. And that's what we're comparing in these graphs. This is the CDF.
Okay, but you sampled from the uncertainty in the Gaussian process emulator.
Yes. Okay, I'm running out of time. People are hungry. Yes?
Emulator is on the final quantity or the travel time or on
The emulator's on the
sparse
travel time.
location?
Yeah. Because they're supposed to be good at that. Yeah. Well, I mean, again, this has been discussed this week. If you wanted to apply the emulator to the solution of the PDE, you have to have as many emulators as you have degrees of freedom for the PDE. That's expensive. Okay, so to summarize, so we've extended this cursive dimensionality breaking result from the best n-term approximation to something more practical, sparse collocation in the infinite dimensional case. We have a general convergence analysis for smooth, countably variate functions. We have dimension-independent algebraic convergence for the right multi-index sequence, and we have adaptive algorithms or heuristic algorithms for finding the right multi-index set. And yeah, and we've shown that the assumptions that we need for this convergence are satisfied for the log normal PDE diffusion problem. What we're looking at right now is verifying the assumptions for other node sequences. If we could use layer points, that would be much, much more convenient, but we haven't been able to derive the bounds for the layer points yet. There seems to be some room in the estimates. Performance is better than what the estimates say, so we're looking at this. And of course, it'd be nice to have a rigorous convergence proof for this adaptive algorithm, which is based on some heuristics. And I'd like to make a plug here for Lorenzo's software. So we've made heavy use of Lorenzo's sparse grids MATLAB kit, which is available for download. This is a very, very nicely written and useful piece of software. Here's some references for our work and some related work, and I'll leave this advertisement up. We have an uncertainty quantification workshop coming up in March in Dortmund. This is the small sister of the SIAM UQ activity group. This is GAM's activity group on uncertainty quantification. We have a very nice list of speakers. The workshop is free, so there's no conference fees, and there's still some inexpensive hotel rooms in Dortmund that are reserved. So there's no reason not to. Thank you.
So we have already had some questions, but if you're asking questions, you sit between us and lunch. So
I want to go back, let me just go back to the first part of the talk. So you extend the indexer,
Yes.
and you extend the grid at the same time.
Each multi-index has a grid associated with it.
Okay.
Yeah.
So
with
if
each
you add,
index set, I get a
you
new grid.
if you add a multi-indexer, you automatically add some additional tensorized grid at the same time. And take the union with the previous grid.
Yeah.
Okay. Fine. I understand.
Your error analysis and your error plots, which went down very nicely, only are focusing on the error associated with the collocation part. So if this is for PDE, you also have spatial error as well. So is there scope for developing a fully adaptive algorithm that can sort of adapt
Oh, sure. Yeah. I mean, that's the easy part. That's been done. The PDE part. Like, we were thinking of developing techniques similar to Martin Eichel's for Hilbert. But essentially, the way you tack on the deterministic part is essentially the same.
you can prove how close your final estimated error is to the true error?
I'm pretty sure. I mean, it's one thing to devise an adaptive scheme which is both in parameter and space. It's another thing to show that it's convergent. So that is, of course, not. I mean, there's a difference between, the result was there is a multi-index set, but you still have to find it. We have algorithms that do that, but we haven't shown convergence of those. Just shown that if you have the right multi-index sequence, collocation can, even for infinitely many variables, converge. It's another task to show that your choice of algorithm for finding that multi-index set will lead to this.
more hunger for knowledge. Yes.
Question. So the first thing, just in the estimates themselves, I mean, Stechkin's not sharp. Second thing is that you also are, at some point, I didn't see it, but you estimate the Lebesgue constant associated with the Hermite points? Because that's also going to be bad.
Yep. Yeah, something like the Lebesgue constant.
But then the other question is, what does the bound look like? I haven't looked at it. The bound on the Hermite polynomial is looked at is building an index set from. So is the set really lower, or are you approximating it as well? So what I mean is the set lower in the Hermite case?
You mean,
Like in the Legendre case, it's not lower.
yeah.
So is it lower?
So the Lebesgue constant we don't have to estimate because it's taken care of by the CNU. So instead of the Lebesgue, we have the L2 norm of the error
Okay,
in the
so-
projection, blah, blah, blah. So that takes care of the Lebesgue constant. It's an alternative. And then if you ask me whether the set is actually lower or we had to add a few extra multi-indices to make it lower, I honestly don't remember. I think, at least in the a priori case, it is, because those BNU that we use in the a priori exploration of the multi-index set, those are decreasing. So we can show that then you have a really lower set. In the fully adaptive, I should have to look at the numbers, I don't remember. Probably from time to time, 1 or 2 extra indices have to be added, but not that many. But that's, I don't know.
So I'm not a big fan of infinite problems. So if I go to the finite case and show those plots too, right, where you definitely have dimension dependence. So if you do the finite case and you pull this theory through, how bad's the constant look?
Come again?
The constant in front of the rate, it certainly will depend very badly on P and on D.
Well, it does. I mean, the rate is dependent on the rate converges to a dimension independent number, but it is dimension dependent. Right? We showed there was a plot with the convergence with n 10, 20, 40 variables. The constant doesn't. The constant I don't know, but the rate is, and the constant doesn't look like, right? The constant doesn't seem to be dimension dependent because all those. Yeah, exactly. But we can discuss this more offline. I think it's useful.
Okay, so let's thank our speakers for this morning.